All right, hi, welcome back to Math 234, which is definitely a math class, not a geography-based one. Up today, what do we have? Actually, first, one second. Back to the math stuff. So up today, we've got unit 12.5, which is where we're going to introduce lines and planes in three space. Which I think today means we're just going to go over the line part of stuff. So we'll do a bunch with lines in three-dimensional space. And then the second half of this section, which we'll cover on Monday, we'll get through planes. So let's start describing lines in space. Mostly the way that we're going to describe them is using a vector that runs parallel to our line and any point on the line to initiate said line somewhere. Because basically, or not basic, vectors are almost already lines as they are. I mean, technically they're not because they're a directed line segment and not a line itself. But vectors do look an awful lot like lines. They just don't necessarily have a point to start in space, right? Because a vector can be placed anywhere in three space and still remain the exact same vector, whereas lines need to have both a line to go through, but also specific points that they pass through, right? If you move a line somewhere else in space, it becomes a different line. Whereas a vector shifted around to a different place, different point in space, will remain the same vector. So just a little bit of semantics to talk about at the beginning. So the first idea we're going to bring up is how to decide if two vectors are parallel. Because that'll be important to us as we start to construct some things. Specifically, we'll say two vectors are parallel as long as one vector is a scalar multiple of the other. So if I take a vector, multiply it by 2, my result is a parallel vector. If I take my vector and multiply it by -1 and just reverse its direction, we'll still consider that to be a parallel vector. So again, they're parallel just as long as there's a scalar multiple that gets us between one vector and the other. Another definition, if we just look at the ratio between components for each component pair in our two vectors, they need to all be the same. So if I divide the x components, divide the y components, divide the z components, and I get something like 3 every single time, that means my two vectors are parallel. But again, it's got to be the same number each time, and probably we need to add some extra notation in here about our denominators not being 0. So W1, W2, W3, all of those need to not be 0 in order for that definition to work. So dividing by 0 is kind of bad. It doesn't mean they can't still be parallel if one of those entries is 0. It just means the corresponding entry in the other vector would also need to be 0, and you would just kind of ignore that ratio when you're checking it this way. Again, the most proper way would be to use the top definition. V equals K times W for some scalar K. And I can see I forgot some hats on those vectors, so I'm going to add them back in. Right? Doing my very best to emphasize that something's a vector whenever it's a vector with those hats. Something else we should mention, vector equation for a line. It's this line right here, or this equation, R of P, the vector valued equation for a line, is equal to some point plus T times a vector. If we try to decipher what all is going on there, how would I want to do that? I have two terms inside this definition of a line for three space. And I want to claim that this thing should look an awful lot like y equals mx plus b. Because both are describing lines, so I want this thing to like be a line as well. But I'm going to change it to be a vector valued function instead of a scalar valued function. But the pieces that make up a line are still mostly present. I have an mx substitution, that's my t times v, or rather v times t, because t is now our x, but more on that in a second. And that r naught, or that r0, should be just a point on my line. Unlike y equals mx plus b, where we had to have specifically the y-intercept, this r naught, or r0 point, is just any point that's on our line. I don't care where it is at all. I just need any point on the line in order to start creating one. Finally, to add the third part to that, if you're reading ahead to see the part that I already wrote in, t is a parameter. Because we are going to be calling these things parametric equations. And if that word sounds familiar, it's hopefully because you're remembering something from Calc 2, because you would have done parameterizations in that class. So again, t is a parameter. And it just means that it's the single variable that we're going to use to describe a line. Because one other element I want to add here. While I might want to talk about this line existing in 3 space, in all 3 dimensions, which means there's an x, a y, and a z component out there, this line is still a one-dimensional object. Right? If I'm on the line, I can only move in a single direction. I can go forward or backward. So if I have a one-dimensional object, that being a line, that's existing out in 3 space, I only need one parameter in order to describe that object. I only need one parameter to describe a one-dimensional object. So I can only go forward or backward. I can't move left or right or up and down. So I only need to talk about moving in one dimension. And so I will call this thing a parameter with, or a parametric equation with only one parameter. And then we're going to contrast that against some other shapes that require 2 or 3 parameters. But for a line, we only need the one parameter, so it's easier to talk about it in terms of t instead of trying to have x, y, and z all be independent variables. Instead, I'll redefine x, y, and z in terms of my single parameter t, and then I can just have one variable running through the problem instead of 3. So we have some new fancy definitions for x, y, and z as their parametric equations. And again, this should remind you a lot of y equals mx plus b. Except that instead of x, we're going to use t as our parameter. And then our point is going to be made up of 3 different components. But all the x naught, y naught, and z naught, each of those pieces, those are all fixed points, right? So if I'm putting a subscript 0 on a, if I'm putting a subscript 0 on a letter, that means it's a fixed point somewhere rather than a variable. So something that shouldn't change. X naught, Y naught, Z naught, all just a point. Finally, we need a couple of other definitions real quick. We'll say that 2 lines are parallel if and only if the vectors that we use to generate those lines are parallel. So it's enough to say 2 lines are parallel by to just compare their vectors. You don't actually need to compare anything else on the line to figure if they're parallel. But we might want to see if lines intersect somewhere in space. Also, if those lines do intersect, the angle between the lines is the same as the angle between the vectors. So again, you can just pull those vectors off. But where in regular old algebra, where we're working in 2 space, we can look at a pair of lines and either say they intersect somewhere because they're 2 lines, they always intersect at a point, or they're parallel, meaning they never intersect. When we step up to 3 dimensions, we can still have both of those 2 cases, 2 parallel lines that won't intersect, 2 lines that do intersect at a point. But we also have a third option, which is 2 non-parallel lines that do not intersect. Because now that we're moving through space, we added in an extra dimension. It's entirely possible for two lines to never intersect, even though they're not parallel. So that new definition for non-parallel lines that do not intersect somewhere in free space is called skew. And you can imagine that these two lines maybe exist in planes that don't intersect. So I could have, like a line, I'm just down here on my table. I could have a line that exists on top of this table, it's sitting up here in front of the room, and maybe it's going over toward that door. I have a second line that's along the floor of the room going up toward the back of the classroom. Those two lines aren't parallel. One goes to my right, the other goes to my front. But they don't intersect because they're separated by the height of the table. So again, we'll call those things skew if that happens. And with most of the rest of today, we're going to look at how to figure out if two lines intersect. And if they do, where they intersect. So let's actually do an example. I've talked enough. Let's figure out L1 and L2. Hey, look, they're describing the same line. Right? Suppose we can start with that example. So we do that. How would I do that? Come back to filling in the theorem later. First, I would probably just go look at their vectors. So if I have lines V1 or L1 and L2, I'll just define two vectors V1 and V2 to talk about the vectors that are in those lines. For vector V1, it is going to be 2, -2, 6. Where I'm getting those values from the coefficients on T in each of X, Y, and Z. I'm pulling those out to establish my vector. How about we mark it in green so that those go together? Also, do the same thing, but for the other line. Come on, there we go. V2. This one looks like -1, 1, -3. -1, 1, -3. Where again, I'm looking at the coefficients on my parameter. But in line 2, my parameter is going to be S, whereas in line 1, my parameter was T. Just giving them a different label so that I can start comparing them against each other. And I think I can plainly see that V1 and V2 are parallel vectors. Right? If I just multiply my blue vector by -2, I'll get my green vector. Alternatively, if I take the ratio between each of the three components, I'll get -2. 2 over -1, -2 over +1, 6 over -3. All of those simplify to -2. So I'll claim that those things are parallel. So no, at least that's the case. If I want them to be the same line, I just need these two lines probably to intersect. That's my guess. So if I set x equal to x, y equal to y, and z equal to z, I'll have something like 1 plus 2t equals 3 minus s. I'll have 5 minus 2t equal to 3 plus s. And I'll have 6t equal to 6 minus 3s. And if I wanted to check that these things were the same lines, I could probably solve each of these equations. See if they all come out to the same number or the same equation. This looks like 2 minus 2t equals s. This is going to be 2 minus 2t equals s. This last equation also 2 minus 2t equals s. I get the same equation each time. That's probably enough to say these things are the same line. If I wanted to take it a step further, I could find any point where these two lines intersect. And because if two parallel lines intersect anywhere, they have to intersect everywhere because they'll be parallel. So again, finding any single point ought to be enough to claim that they're parallel. And I don't know, let's pick some numbers. How about, since it's all the same equation, how about S equals 0, T equals 1? So I made just one choice because I got the same equation every single time. So I have what we'd call a free parameter or a free choice variable, meaning I can pick a definition or I can pick a value for one of my parameters. In this case, I chose S, and then figure out what the other parameter has to be in terms of that. Again, I just kind of decided on one. 0 seemed all right. So I'll look at R1 of 1 and I'll look at R2 of 0 and probably see that these lines are the same. If I plug in 1 for T, I'm going to get 3, and then I'll get 3, and then I'll get 6. And if I plug in 0 for S, it looks like 3, 3, 6. Cool. So I am going to claim that's enough to say that these two things are the same line. Anybody watch ahead to see what two words fill in these blanks? If not, I'm just gonna guess that we wanted to say they are parallel and they intersect. I know that that's good enough to call them the same line. So that's probably a pretty good guess as to what those two words were. Might not be exactly what's in the textbook, but again, good enough to get a solution. Let's take that. Cool. The equation of a line segment is going to be this fancy looking equation that I'll go talk about in just a second. But first, I want to just look at a couple of diagrams to sort of emphasize how we're describing lines in space. Because the way that we describe them with vectors is a little bit odd. But here's basically what we're going to do. If I want to describe a vector that's out in space, or I want to try to describe a line that's out in space, excuse me, using some vectors. We have that R0, that R naught, which is really just the position vector to some point. Right? So R naught is that magenta one that's just drawn in there. And then our green vector V, that's the little guy down there, determines the direction of our line. No, that's not a very high resolution picture, is it? Enhance by zooming out a little bit. So that when we construct our vector equation R, it is going to be a infinite series of vectors that are all going out from the origin to all of the points that are on the line. So the vector equation that creates a line is really just a whole bunch of the blue vectors shooting out from the origin that end up somewhere on the line. The thing they create is the line, so it's usually best to like think about the line just as that object that's out in space. But at least once it's worth looking at the actual vector definition of how the line gets generated. So it's really just go out the position vector to any point, so go out along that magenta vector, and then just add in some multiple of the direction vector v, which slides us out along that line in either the forward or the backward direction, depending on which way t goes. But really, if I'm adding two vectors together, which is adding the pink vector and some combination of those green vectors, they create the blue vectors that still stem out from the origin 2 points on the line. It's a little bit of a weird way to think about the line, and it can take some amount of brain power to wrap your head around that concept. Uh, but I suppose I'm throwing it out there because it's worth knowing about. Yeah, so there it is. But back to the next thing that we want to talk about. I want the equation of a line segment in its generalized form. And it's probably going to be easier to talk about this thing if I have an example. So why don't we do that? Ta-da! Cool. Here's a line segment. Let's put a couple of points on here. How about terminal points, which will claim this guy here is 5, 2, 0, and an initial point. How about in red? We don't use red that often. Take it back. Blue. Claim that's 1, 2, 3. So my line segment, it just goes from one point to another point, and it's in a straight line. Line segment. Really fancy with our definitions today. We've got a real funny looking definition up here that I maybe want to add some color into. Because I just want to go between my 2 points, which I'm going to call R0 and R1. It's 2 fixed points somewhere out in space. And the idea behind creating this line segment is that when t is equal to 0, I am at my initial point. And when t is equal to 1, I'm at my final point. So in order to do that, I'm just going to multiply in two different versions of t. I want 1 minus t multiplied into the blue point, so I can see if I plug in 0 for t, I just get 1 times r0, means I'm exactly at that point. And then also plugging in t into the orange part, 0 times r1 means that that whole term is 0, so it's gone. So if t is equal to 0, my vector equation just returns r0, my blue point. T equals 0, vector equation only returns the blue point. And if I plug in 1 for t, now 1 minus 1, the blue term is 0, but 1 times r1, the orange term is just r1. So when t is 0, I get the blue point. When t is 1, I get the orange point. That's sort of the basic idea behind the construction of this line segment equation. The rest of it is I just want it to scale linearly in between the 2 points, which this thing is a linear equation because all I did is multiply in a couple of linear terms. So the rest of it generates the line segment for all of the points in between those two if t is any number between 0 and 1. The real fun part about these line segments is that there are an infinite number of equations that I could write to make this equation work. There's no specific constraint that t must go between 0 and 1. If I really wanted to, I could have t go between 0 and 10. If I just wanted my parameter to be larger. It's just, if we're thinking about the easiest way to generate a line segment, it's like, okay, let's just have t be in between 0 and 1. If it's at 0, it's at the beginning. If it's at 1, it's at the end. And then the rest of the numbers will just fill in the segment. So that's why we generated the line equation the way that we did. It's its first form, where it's just, here's 1 point, here's the other point. 0 and 1 puts us at either endpoint. Any number in the middle puts us somewhere in the middle. But you can also multiply that thing through to have the other form of a line segment, which is just our initial point, r naught, plus t times the vector that gets you from one point to the other. So if I wanted to come make that equation to get between these 2 points, I might write it out something like the following. R of t. Oh, and as I started writing again, I realized I didn't put hats on any of these vectors. That wasn't very smart of me. Okay, there we go. All of those r's are vector valued things, so they get hats. So my vector function, r of t, is going to be my initial point where I want 1 minus t times r1 or r0. So I'm going to highlight this one in blue. That's 1, 2, 3. Plus t times my orange point, 5, 2, 0. And that gets me the equation of the line segment. If we're comparing this back to some stuff in algebra, since that's the other class I'm teaching right now, and it's kind of fresh on my brain, this would be like our equivalent of point slope form. We've got our two different points show up directly in the equation, and then we just attach a couple of slopes to them, 1 minus t and t. If you wanted this to be maybe in a slightly different form, I don't know if it'd be more or less workable, but you could combine them together to look something like 1, 2, 3. Still that blue point, plus t times the difference between those 2 points. So the vector that gets us from blue to orange, which I believe is going to be 4, 0, -3. I add in maybe a little bit more color here. That is the vector that gets us from blue to orange. So that's the vector that moves us along the line segment. And to completely beat this dead horse, I can combine those two vectors into one vector and call it 1 plus 4t, 2 plus 0t, and 3 minus 3t. So 3 different forms for the same line segment. Just choose the one that suits you best or that's easiest to come up with. All right. So on to our next example. Finding parametric equations of the line that passes through the points 2, 3, 4, and 1, 0, -1. Well, let's see. If I wanted to find those points, I want to find something over here. I want to do a minus b. How about a minus b? And I'm going to call that my vector v that I'll use to generate my parametric equations. So a minus b, that's going to look like 2 minus 1, 3 minus 0, and 4 minus -1, which I think is going to be 1, 3, 5. And from there, I just need my 3 parametric equations, which are x, y, and z. So I'll have x. I just need to initialize this somewhere. Let's start at b. It looks like an easier point. X is going to be 1 plus 1t. Y is going to be 0 plus 3t. And Z looks like -1 plus 5t. And just to further emphasize, I could have also called this 2 plus t for x, 3 plus 3t for y, and what else is that? 4 plus 5t for z. Actually, you know what? Let's not call it t the second time. Let's call it s, just so that it's a different parameter, emphasizing that they wouldn't be the same parameter exactly. Either one of those set of parametric equations works for this line, right? I can initialize my line at either point. Really, any point on the line will work. But I'm going to use one of the ones that I was given because that'll be a lot less work. And I do want to be as lazy as possible. So I do it that way. At what point does this line intersect the xy plane? So the xy plane, that's going to be when z is equal to 0. Right, that is the xy plane. So if z is equal to 0, I'll just set 0 equal to my parameter or my parametric equation for z. So -1 plus 5t equals 0 means t is going to be 1/5. And then I will use that value of 1/5 to find x and y. So x is 1 plus t, which means it'll be 1 plus 1/5. Y is just 3t. So 3 times 1/5. Where I'm getting both of those by taking this 1/5 and plugging it into each of those equations. So I just need to simplify this thing. I think that's 6/5 and 3/5, giving me a point of 6/5, 3/5, 1/5. Nope, 3/5, 0. Right? Not 1/5 for z. 1/5 was just the value we got for t, not for z. So just careful with that. The whole point was that this point is in the xy plane, meaning that z is equal to 0. So just careful that you don't accidentally plug your parameter in for exactly one of x, y, or z, unless that's what your parametric equation tells you to do. Right. And one more thing here. We want to take the two lines, R1 and R2, and say that they intersect at 2, 0, 0. I want to find the angle between the lines. So if I want to find the angle between two lines, I know that the only thing I really need are its vectors. So I just need V1, which is 1, -1, 2. Grabbing it here, here, and here. V2, which is -1, 1, 0. From that and this no thing there at the end. And then if I want the angle between two vectors, I'll probably rely on the dot product version to say that theta. Okay, well, specifically, I should say that cosine theta is equal to v1 dot v2 divided by the magnitude of those two vectors, v1, v2. I've been really bad at my hats today. Let me just go add all those back in. Hopefully I didn't miss any examples earlier. Which I can then convert into saying that theta is going to be the cosine inverse of what I get when I multiply all this stuff together. Well, okay, if I take a dot product, 1 times -1 plus -1 times 1 plus 0 is -2 divided by a couple of square roots. I believe that's the square root of 6 for the green vector and the square root of 2 for the blue vector. And then you could plug that into a calculator to figure out what our angle is. Just looking at the thing that I'm going to plug in here, I'm expecting an obtuse angle since I'm going to take the inverse cosine of a negative number, which if I'm looking for the angle between two vectors, then that would be fine, right? Angle between two vectors can be, it can be an obtuse value. However, where did I just throw? Ah, my pen is gone. Where'd it go? Oh, there it is. Magnetized itself to the overhead projector. For lines, that's going to maybe not quite be the case. And if oh no, I haven't put the weekly review in the right spot. 1 second. Freeze this for a moment. Oh wait, no, that's just going to project everything to well, whatever. We do it live. Nope. Nope. Back to here. Yeah, there we go. So if I look at the intersection between two lines, right, I can see that there are two angles that are going to be generated, being these two angles here. I'll call them theta number 1 and theta number 2. Anytime two lines intersect, they'll have 2 points of intersection, but if I were to just look at their vectors, I guess that means I need theta 2 to be a different color. What have I not used? Orange, cool. If I look at the vectors that I generated here, was it that angle? It was, I think. If I look at my two vectors, they intersect at a very specific angle. Only one of the two options. So my vectors intersect at that obtuse angle, which I know is going to be obtuse because I ended up taking the inverse cosine of a negative number. But by definition, we're going to say that when two lines intersect, the angle that's between them is always the acute angle. Because there's always going to be two options we can choose for the intersection between two lines. I just want to claim that it's always the acute angle for the intersection between lines, even though vectors themselves can intersect at larger angles. Which means we need to go through and fix our definition. In particular, I want to be taking the absolute value. of my dot product. Because that'll then force this arc cosine function to spit out an acute angle. So anytime I take the inverse cosine of a positive number, as long as that positive number is less than 1, I get a solution that's somewhere in the first quadrant. So in particular, this has got to be theta number 2 that we're going for. The orange one. So if we're looking for the angle of intersection between two lines, again, it has to be the acute angle. So we're going to be taking its absolute value. From there, you can plug it into a calculator, get a number. If someone's got it, feel free to shout it out and I can write it down. But otherwise, we're fine to just leave it like that. 1.955? Is that what I heard? Awesome. Sweet. We got a number. Love that for us. That's going to be in radians. I can tell because it's a really, really small number. You almost always, and you almost never end up with an angle that's less than 1 degree. We're working in reasonable spaces. I should probably talk about one last thing on this problem. The intersection point. The problem told me it intersected in 202, but I didn't use that point at all to figure out this angle. So I suppose the question is, does that mean the intersection point was completely not important? Or did I need to include that element of the problem to claim that they intersect at 202? So, some of my thoughts there. I didn't need the intersection point. So maybe your first instinct is that that intersection point was irrelevant to the problem. I didn't need to know that they intersect at that point. And that's like half true. I didn't need to know where they intersect in order to solve the problem, but I do need to know that the points intersect somewhere, right? In order to have an angle of intersection, I need my lines to intersect. So I do need to be told, or at least to figure out, that these lines intersect somewhere in order to find the angle of intersection. But the exact point that they intersected at, I didn't really care about that part. Didn't need to know they intersected at 202. I just needed to know that they intersect somewhere. It's a fun extra little element there. And right, there's a whole other bit here that, oh wow, there's 2 whole pages. All right, 3 minutes, lightning round. Let's do this as fast as we can. Okay, let's find the distance between some point and a line. Best way to find the distance or the shortest distance between a point and a line is to go in a straight line. So go right at the line, which means that I want a 90-degree intersection right here. And hopefully this diagram kind of looks like some things that we already did. Namely, if I find this angle, I think it's 14 degrees. Yeah. If I draw in a yellow vector right here, switch this over to a 76-degree angle, draw in a pink vector right here. Hey, come back. These should hopefully remind us of a couple of projections, where this pink distance is the orthogonal projection of something. This yellow line is the regular vector projection of something. In both of these cases, I'm projecting onto the vector v, which is the parallel part of the line, the vector that tells me what the line looks like. And the thing that I'm projecting onto there is this vector SP, defined by the problem over here, or defined by the way that we set the thing up. That vector, SP, is just any vector, or it's a vector, between any point on the line, S, and my point in question, being P. That point S that's on the line doesn't matter at all. I can pick any point that's on the line because all I'm really going to care about is projecting that vector somewhere. In particular, I want to say that D ends up being the orthogonal projection or the magnitude of that orthogonal projection of V onto SP. But I could have also defined it by saying that it is. It looks like it is SP, this magnitude, times the sine of theta, because I'm just projecting it over to the other side, which should also start to remind us of the cross products, which I'll skip over a couple of steps. But effectively, what we're going to do to find that distance is to get the magnitude of the cross product between V and that SP line and divide it by the vector, by the magnitude of V, which means I forgot the magnitude part right there. But since we are totally out of time, thanks, Tradle, I will finish this example on Monday. But if you're looking ahead in the homework, here are the two equations you want to use. Okay, bye, 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 bye. Hey. All right. I had a pretty good question right after class, so I'm going to make a quick addendum to some of the stuff we were talking about in lecture today. Someone was confused as to why these points over here all of a sudden became vectors. Like, what's happening there? Right, I have my point 1, 2, 3 that suddenly becomes the vector 1, 2, 3. So what's happening here? 1, 2, 3 is a point, but its position vector, which is R0, the vector that's highlighted in blue right up here, that R0 is a position vector that goes to the point 1, 2, 3. So if I bring that back over to what this picture is looking at here, I've got my point P0, which in this case, pretend that says it's at point 1, 2, 3. The position vector is that pink vector you see in the middle. It's the vector from the origin out to the point. So oftentimes when we want to talk about points in space, we'll use their position vectors to locate them. And so when you see a point get converted to a vector, that's because I'm using its position vector there. Okay.